In this demo, I will demonstrate the capabilities of the CogniMem CM1K chip with the CogniMem V1KU camera to recognize several different types of characters from the different languages without any custom programming using the Freescale development board. I will be demonstrating the functionality of the CogniMem chip using a .NET program ported to work on the Freescale platform under Linux operating systems. The components of this demo include a Freescale IMX53 Quick Start development board with the default Linux image and camera driver installed, a CogniMem V1KU camera which consists of a lens and the chip mounted together, and a USB hub to provide keyboard and mouse connectivity. Let's get started. We will begin by firing up the simple image recognition application. I'm going to demonstrate the use of this application to teach the CogniMem chip the American alphabet, characters A through E. Then I will teach the chip to forget what it has learned and teach it 5 kanji characters. The first thing I will do is capture a sampling of the American alphabet printed on a piece of paper with the camera. This button gives us the ability to capture a live feed from the camera and display it in the viewing window. The device is capable of capturing 1024 neurons, which is expandable. I will begin by setting up categories to which we are going to train the device. Since I am going to teach it to learn the first 5 letters of the alphabet, I will label categories 1 through 5, A, B, C, D, and E respectively. I can adjust the region of interest, which is the size of the square box which will be used to focus and capture each model. Once I am satisfied with the settings, I will save them. At this point, I have a 32 by 32 pixel block with which to capture our models. So the first thing I will do is start by capturing a representation of an A on the page. I will select category 1, which I have defined as A. I can choose to have any number of categories. I will place my region of interest on the letter A. Like the human brain, when it is born, it has millions of neurons, but no knowledge of what they represent in the real world. I'm going to associate these categories to images and in essence teach the chip the character set. So I focused on the A. You'll see up here on the top what will be captured and stored in the neuron as a model. It will be stored as a 256-byte vector. I will click the Learn button. At this point, I have retrieved the first neuron and displayed it as a model. Each time I train it on a specific feature, you will see the neuron usage increase at a level of 5 per feature that I teach it. It increases at a rate of 5 because I have a feature enabled, Known Nearest Neighbor, which takes additional samplings of the target area, displays several pixels to provide a more accurate sampling of the target area. This way I have 5 samples of an A from different perspectives. The user can set the number of additional samples to be taken, thus increasing the number of neurons used while increasing accuracy of the learned sample. Additionally, this option can be turned off if needed. Like the human brain, you have a finite amount of neurons to fill, but this device allows multiple memory expansions which increases its neuron capacity with no limit and no reduction in performance. Let's make sure we have taught the device the character A successfully by testing other A's on the page. You will see at the bottom of the page that the application has successfully recognized the A on the paper as a category 1A and returned its value in the red. At the top of the screen, you can also see the feature, which is currently under the focus area, and the learned model which was fired. The application is letting us know that it knows the answer, and it is correct. At this point, the chip only has been taught A. It has no knowledge of B, C, or D. If I try to read a B, you will notice it returns a model of A. This is because A is a very general shape and shares many shape characteristics with a B. We will now teach the device the shape of a B, at which point it will learn to differentiate what a B is and how it differs from an A. Like a child's brain, looking at the alphabet for the first time, it cannot differentiate all the letters accurately, and only through being taught can it learn what each shape is and how they differ. As you begin to take additional samples of the characters, it will begin to refine its understanding of them and recognition accuracy will improve. It is not uncommon for similar or complex shapes to require several learned instances utilizing several samplings and therefore neurons. Now that all 5 have been captured, we can do a little testing. We see here the letter E is being recognized as a null object. We will ensure we are using the correct category and train it again, giving it additional neurons to pull from to aid in recognition. I will continue to help it to learn by giving it more samples. As additional samples are added, the recognition continues to improve. We will now swap the page with the kanji characters and tell the application to unlearn what we have taught it so far in this demonstration. We will begin once again by defining our categories. Similar to the first demonstration, we will use 5. We will define category 1 through 5 as form, sword, active, paper, and think. We will now begin capturing the images by placing the region of interest on top of the form symbol and associate it with category 1. I will now move it in front of sword and train it to category 2, and the same for active and paper, and lastly think for category 5. Now this character here looks very similar to paper, but is not paper. We can teach it to learn that this is not paper by clicking the Forget button. You will see it is now blank. Like learning, you can use multiple samples of unlearning or forgetting to refine the process. By continuing this process, you can continue to refine the recognition process based on what has been taught to be the right character and what has been taught to not be the right character. These techniques are meant to be used together for best results. As the device is trained, like a human brain, it learns and adapts to the input you have provided and will return consistent results from complex images and patterns.